So, hello everybody. I have the honor today to do the first talk of this day here in this room. What we were talking about today is, as you see and also saw on the agenda, I guess, is vector databases, which is a quite hype topic that we have at the moment. And yeah, I actually hope that you will learn something today about this new technology and maybe get some ideas where you can use it and how you can use it in your next project or maybe in some projects 10 years ago, because it's really an quite new technology that we are using it. And I also step a little bit what comes after ChatGPT, because we will of course have a little bit of chat of ChatGPT. You cannot have any talk about anything without talking about ChatGPT nowadays, I would say. Who am I that I'm standing here in front of you and want to tell you this? That's me, Erik Bamberg. Looks prettier in natural, of course. But yeah, I'm a principal software engineer, working mainly with Java, 24 years. I do other things, musician, do some indie filmmaking. In my spare time, I'm exploring everything about AI, ML at the moment. This is why I came across the vector databases and learned these things and always open up for new challenges. And the vector database was definitely one of the new challenges that was around there. That was me. Now about you, what hopefully you will learn today when you're leaving this session after the 60 minutes that we have today. I want to teach you today what is vector similarity search in a high-dimensional vector space. Vector similarity search in a high-dimensional vector space. This sounds pretty cool. This sounds really cool. I actually chose it because usually when you're on a conference, you go home and your wife asks you, what did you do? Or your boss asks you, what did you do? Oh, I found this new UI framework and it was quite great. And you get asked, oh, didn't you do this last year or next year? I said, yeah, quite, but it's quite a little bit similar. When you go home after this talk today, you can go home and when you get asked what you learned today, you can say, I learned vector similarity search in high-dimensional vector space. How cool was this? Yeah, and you will get a good feedback with this. Hopefully, you will learn this. All of this is not so complicated as it sounds. Let's jump into this and see what this means. Vector similarity search. What is in vector similarity search, and what is in high-dimensional vector space or vector space in general. Let's jump into this and see what we can do. But first, ChatGPT, you have to mention ChatGPT somewhere. Who of you using ChatGPT in projects nowadays? Well, quite a few of you. Did you find some solution for some limitations like the maximum token size from ChatGPT? I think it's not so worst today with ChatGPT 4 that we are nowadays. How do you bring your own data into ChatGPT? Have you found some solutions for this? Yes, and using your own data when you're talking to ChatGPT in your own prompts? You do? Yeah, there was just one hand as I saw. Before this we had, I think, maybe 20 hands up and one left who overcome this. Yeah, ChatGPT have some limitations if you're using this. One of the limitations is definitely the maximum token size that you can use in ChatGPT. People say, oh, there are a lot more now, 32,000 or even more now with a new version. I did a little bit of the math and was thinking, the ChatGPT limitation, 32,000, oh, that's great. If I take a Harry Potter book and I put it into these tokens, 32,000 tokens, that is approximately 50 pages of Harry Potter. If you take the second Harry Potter book and ask some question about spiders in Harry Potter book, you will not get an answer because these are not appearing in the first 50 pages of Harry Potter, for example. So I think it's a lot, but in general, this is quite a limitation that you have when using ChatGPT. The other limitation is, of course, if you have a big database, you have a lot of products, for example, and you want to ask ChatGPT, you create a prompt about this, give me this information about my database. What's happening then is you actually, of course, have to bring your data into ChatGPT and tell ChatGPT, this is the data, please execute the prompt on top of this data. You have to bring this data. And if you have a lot of data, again, token limitation, again, you have to bring your own product to a third-party product like ChatGPT on the internet. It sounds a little bit like a limitation. I will show you now what vector databases is, and then I will also show you that we actually can overcome all this limitation of ChatGPT, the two that I mentioned, with using vector databases, which is one of many, many cool use cases of vector databases. Why we're talking about vector databases and ChatGPT? When I look into ChatGPT and I look into my email and look all this newsletter that I have subscribed to, which is quite too much, I know this. When I look into this newsletter, I see, of course, ChatGPT is one main topic on all this newsletter, but another thing is popping up more and more on this. I found there are some companies that got really big fundings at the moment. For example, there's a company called Pinecone that gets 700 million Series B funding. Chroma got 18 million seed funding. A company, open source, Weaviate got 50 million Series B funding. Mile was 60 million Series A fundings. And I was thinking, is all those companies get so much money from fundings out of nowhere, even open source companies? I was thinking about what they are doing. What are these companies doing that people are willing to pay them the money to doing more research and doing more development? Because usually where the money flows is actually which will be the next hype on technology. Not always, but very often it is. So I had a look into what are these companies are doing? Why are they so important to many of these fundings? One thing that all these things, what they are all doing is, of course, they are all building vector databases, doing research on this and building out vector databases at the moment. So the question is, why do we need another kind of database nowadays? Why will this be so important? We have all these databases. We have relational databases. We are all familiar with this. They are very good to store structured data. We can run ad hoc queries on relational databases. Very good in this, transactional things, very, very good. The next generation came with new SQL databases. If you want to scale out horizontally, key value base and everything like this, resilience, replication sets, all the things, NoSQL databases, very good in this kind of data management. Another one is, of course, graph databases. When I give the first time this talk, there were a few people in the audience who asked, oh, is this like graph databases? No, vector databases is not like graph databases. Graph databases are very good in complex relationships. You can use for dribble store, semantic web, everything like this. Everything that is hierarchical and is kind of a network that you have trees, you can very good store in graph databases and querying this. So a lot of data is covered already with all those databases kind. But now comes another one, vector databases. What gap does they fill? They are filling the gap of unstructured data and doing a semantic search on unstructured data. This is something that the other three categories of databases are not able to do nowadays, or at least they are not very good in this. Vector databases is all about storing unstructured data and doing a search on this unstructured data and combine this with structured data, of course. What is unstructured data? When we talk about unstructured data is very important because it's around 80% of all the data that we have nowadays in internet, in companies are really unstructured. Unstructured means you have documents in your company, PDF, Word files, everything like this that you have in your company. They are unstructured. This is just text for a computer. Yeah, you don't have text on that. It's just text. You have in the internet a lot of video information. Audio files are unstructured data that we have nowadays. Images, of course, if you have to do some images processing, medical use cases, for example, in hospitals and so on. These are all unstructured data that we have. And this makes up around 80% of all the data that we are storing at the moment on the whole world. Just 20 of this approximately are really structured and can be handled very easily and nice with relational database systems, for example. So we need a way to store this data because this is something, we have it and we want to search over this, we want to querying this, we want to get new information out of this. What we usually do in RDBMS nowadays, if you store the data, one way to store them is to tag this data. This is one solution that we have. You have some pictures, for example, just as an example of unstructured data. And if you store in a database, you put a tag on this. Say, this is an image and this is a cat. Have a look on these images that we see here. This one and this one. Just go into yourself. Just think a moment just about if someone asks you, you have to store it in a database, please put in a list of tags for these things. How would you tag these two pictures in your database? I'm pretty sure every one of you comes up with a solution. But if I would go around here and ask every one of you, I'm pretty sure I will find from everyone a different list of tags that you have chosen. Me, for myself, I would say, this is a cat. I would maybe add a tag like orange when I want to find all pictures which are in an orange color shape. I would say this is a cute cat. Maybe some of you have also chosen this word cute with this. Someone said, oh, there's a white cat. In my opinion, he is also very cute. I would maybe also tag him as very cute. Other will say white animal, household animal, pet, something like this, tags that you choose. When I ask everyone, pretty sure we will find very different approaches. And this is really the problem with storing this data on databases. The same is for documents, for example, that you want to stay. Everyone is tagging different. You have a team of 10 people. Their job is just to tag unstructured data. The team of 10 people will come up with 10 solutions over the day for the same data. This is really a problem when you're storing this data. So we have to overcome, we have to find a solution for this problem, of course. And nowadays, every time my boss asks me, is there a solution for a problem? The first thing that we are thinking about is, yeah, of course, there might be a machine learning model that can do this. And this is one of the first things that we think about. Maybe not. But there is a solution with machine learning models for this. If you have unstructured data, we have nowadays really pre-trained model that can actually do the trick and take some unstructured data, like these pictures of this cute orange cat that we have there. You can use machine learning models, and the output of the machine learning model will be a so-called embedding. This is actually a vector. You see, this is some kind of an array, a lot of dimensions in it with numbers. So the machine learning model is able to convert an image that you have into an array of float numbers that you want to process. And this is something, these float numbers, that you more easily can store into a database than a picture of a cat. And this embeddings contains all the labeling that I come later to this, what the machine learning model is in. So there is a way you can use machine learning models to create a numerical representation of unstructured data. And the good thing about this is you can have machine learning models for almost anything that we have on the world. We can have this for simple words. When you have text, sentences, we will find machine learning models pre-trained of creating this image this embeddings representation from images, from videos, audios, documents, everything like this. The machine learning model itself is usually doesn't care about what is the input as long as you can transfer it in some numbers, and you will get out some embeddings. out of this. So the point that I want to take over is it is really for every of the unstructured data, we have some machine learning models. And the good things nowadays on Hugging Face, OpenAI, whatever you call it, you will definitely also find pre-trained models for this. Vision, WesNet, AlexNet, text, BERT, Disselbert, all those kind of things that we have to create this embeddings. The point is even source code. I just came across a problem, and I even found out there is a machine learning model that can put Java source code in, and it turns you an embedding, as means a floating list of arrays that's represented the semantic of this different source code that you have. Now I said the bad word semantics. You might say, okay, this is numbers, but what does the number mean? What is better on this number than my tagging that I did before? Where usually I use words and I can understand it, but now we have a list of numbers. Why does it matter? These embeddings have a very specific thing. What the machine learning models are doing on the training is they are putting the data that is the input data into a semantic context that you have. So you are training your machine learning model, or it is pre-trained for you over all the iteration, all the epochs that you're training your model. And in every of this iteration, the machine learning model is getting better, and in the task that you have to do, I will show later on what this will be, and it will learn on the training process how different things in our world fit together, where they are fit together in the same context. Let's have a picture. Before the training, we have the New York, USA, Japan, Tokyo. We are running and training on machine learning models. The machine learning usually picks up the data and try to sort it out and combine and put them together into group. They're grouping it together. They're clustering it. So you will see, if you look into the output of machine learning models, you will see that, for example, it will end up with putting the name New York and USA in a context close to each other. Here it is on the left side that we have. It put it together. On the other hand, it will separate Tokyo and Japan from these things, putting it on the right side here. In the same time that we are doing this, the machine learning model will automatically find out that the USA and Japan is their countries. They're related to countries. New York, Tokyo are city. So it will separate it somewhere else. These are just two dimensions that I have, the x and the y axis. Let's think about all the things happening with, let's say, 500, 700 of such dimensions that we have. This is x and y. We can have z, and we can have a machine learning model. We have 500, 700 of this dimension. And it really goes on and put all this information that you put into this context and put things together or near to each other in this array, in this embeddings, in this vectors to where they belong. We will end up with something like, we can see in our sample that the cute cat and the black cat will be close to a tiger, for example, in the representation, if you're really visualizing these numbers. So we have a cute cat black that will close to the tiger. And we will see that, for example, if you put in a monkey, it will close to the tiger because it's also an animal, but very far away from the cats that we have before. Banana trees, some kind related to monkeys, will move in the direction of the monkey itself. So what is good is really clustering unstructured data. And we see this unstructured data we can see this as an n-dimensional vector space at the end. I will show you an example later on how this really looked three-dimensional. How is this possible? This machine learning model, just very quickly, can actually understand the context of the data. How can it understand the context that two words are semantical close to each other, while other data are semantical very far away from each other? Usually there are few things where the vector can be used or something like this. Just a little example, if you're using, for example, a bird, it works usually in the way how you train bird model. You are asking, you have a sentence like, I have watched this movie, it was awesome, and you're masking out parts of this and ask the machine learning model, please fill out this missing words inside of this. We will not use one word, we will 15% of the words or something like this. And the machine learner will learn over all iteration how to fill out the word. It will learn that in the sentence, if I've watched this movie, it was awesome, that the words very likely in your context will be movie. Yeah? And if you learn at the end, I watched this Marvel movie, it was terrible. If you learn always you're saying terrible or Marvel, it won't like you terrible and not, no, I was just kidding. This is how it works. Yeah? To train a model and in order to really fulfill this and to find the words and really fill the gaps, the machine learning model have to learn the context of this. It has to learn that a Marvel movie is usually terrible, and that awesome and movie maybe is used together in the same context. Might not be the best thing, but I think you got the idea of how this training works, right? It is very hard to understand from time, and it's very hard to visualize in your brain when someone's standing in front of you and telling you the things and so show you some two-dimensional lines and some words about monkey and apes. Happily, we had from Google Labs created something 6 years ago that can help you to visualize all those things. This is Projector TensorFlow. Unfortunately, I found out that I'm on the wrong screen. Here we are. Just to explain a little bit how it looks like, it's very good. It's just taking all the words that machine learning models had been trained on. This is from words, and it tries to visualize this in a three-dimensional space using PCA to limit it, to calculate it down. And this is actually words that are trained on word-to-vectors when we are doing. It will be quite challenging because I have to check this in. Let's say to see how a context works, what the context is. Let's try to search a word here. Let's say I'm searching for the word, let's say king. And I can really not see it. Did I change it? There was on where I can add how many words is this? Here we come. Let's say we ask, let us visualize when I'm looking for a king, which are let's say 10 words that are close to a king here. This actually does not really work on this screen here. Yeah. I actually don't get that I was looking for a king. Forget about this. What you usually will see that the word king will be very close. If you're looking for the next 10 words which are close to king, you will find something. I don't know why it's not working here now on the screen, but usually you will definitely see on this representation that on king, the next things are throne, queen, empire, I think also United Kingdom. Charles is not yet there, but maybe it will come up when it's there, we training this model. So just wanted to give you an overview about how this looks like in a three-dimensional space and what actually is a three-dimensional space here. but you can definitely projector.tensorflow.org, try it on your own and at home, and you will see that there is really this representation, and this will end up very close to each other. Let's go back to our presentation. This was this visualization, which actually obviously didn't work. When we have this embedding and we have created this embeddings with a machine learning model, usually you can also, of course, will need to have some more data that you already have structured data on side of this. If you have pictures, for example, you have the embedding of this picture of the cat that we have, but usually you also have structured data that comes along with this unstructured data. For example, here we have the name of the photographer, in which year this photograph has been taken. In this case, 2060. You have, usually in the real world, you have already structured data along with some unstructured data that you're using. And this all unstructured data, of course, you can put together and have this embedding that represents this image and in this semantic context, and you have all your structured data. You put this all together and you have some kind of combined data. The question is, what do we do now with this new findings? We have embeddings, we have the structured data on top of this. We know that the data is in a semantic context. Now the question is, the big question is, what do we do with this? I'm an old school developer. When I have some data, the first thing I do I store it in a database and deal with it later on. And this is exactly why we have vector databases and what vector databases are for. If you have this data with the embeddings, with the metadata to the structured data, you can use this a vector database actually to store this data inside a database. And of course, we can find it again after we stored this. And this is a very, very cool way. Let's say we have all those embeddings this in a vector space. We are stored. These are all the blue bubbles that we have over here. And what we can do now in a vector database is a really cool thing. If I have another, let's say, document or another image, another word, whatever our unstructured data is, we can also create an embedding from this data that we now have in hand. And we can ask this database in a query, I have this image. It looks like this in an embedding, using the same machine learning model, of course. And you ask the database, what are the other images or documents that you have stored which looks quite similar to what I have here in my hand? So you are putting in this new embedding into the database in a query and say, this is my query embedding. Please give me the 10 most relevant documents, images that you have stored in the database. And it looks in this vector space and actually will find the things. Let's see, we have here the cat, we have an image of dog in a slow. You can have a semantic search and you say, Eiffel Tower by night is close to Paris. I did the test myself. If you're looking for Paris, you will come up with results like Eiffel Tower by night. I stored, for example, in a vector database in a presentation that I did before, images in a database with Eiffel Tower by night, by day, and their machine learning model also is trained on doing the same thing for text. And actually what you can do is, if you're looking for Paris, the machine learning model knows usually that Paris and Eiffel Tower are related somehow to each other. It cannot find maybe pictures of Paris, but it knows, oh, there's a picture of the Eiffel Tower, and they are related. If you're asking the vector databases to find, then for Paris, it will give you some information about pictures of Eiffel Tower, because it's the closest what it have in the database. I will show a few use cases later on that shows how you can utilize this. This is just a little bit of mathematics. I will think we are skipping it. How they find the embedding. If you put it in a vector database in a query, if you're just using some mathematics, close similarity function or Euclidean character, these are mathematical functions that are just calculating the distance between these arrays and between these embeddings that you have. And it will just calculate the distance for all embeddings that are in the database with indexing, of course, and then it will return to you the one that are closest to the result that you put into this. And this is usually very, very fast. First tried, I would say, oh, they take ages to query if I have trillions of vectors. Actually, it turns out it does not. The results comes back usually in milliseconds in vector database, and that makes it really, really cool. They're using a few tricks. If you're looking for this object in the vector database, they usually not give you the 10 closest results, but funny as it is, they are using some approximate nearest neighbors, so they're tweaking a little bit, so they it's not exactly the 10 closest. It might be that one is a little bit farther, and they are approximating the results a little bit to be faster. You have to know this. And the other trick that they are doing in the vector databases, someone asked me, why can I implement it by myself? Because of indexing. The other trick they are doing is in vector databases, of course, they're using indexes like every database. You cannot use a B3 index or something like this, like a relational database on this embeddings, of course. They have implemented some new index methods or other index methods, like ANSW is one of this where they're using the tricks, so they have layering of indexes, and when you're looking for an embedding, they are actually have on the whole databases a layer where they just have a few of these indexes, and they look, oh, the new search index is closest to the left one, and then they're going one detail level deeper and say, from this one, they have another layer where say, when I'm here, the closest one must be here. They go one level deeper, so you usually have 5 levels or 7 levels, where they are going through some kind of limited vector spaces until you reach the full vector space and they know what it is. This is some trick that they are doing so that you get a very high performant result set, and this really works in milliseconds. Where we are in time. Actually, we are pretty good in time. I think so far a lot of information, but I think you got an idea what this is from vector databases, what an embedding is in this vector space. Dominic, some noddles? Yeah, it seems we are here. When you're thinking this is interesting, I have to shorten this, there's way more about this. You might think, oh, how can I utilize this in my company, in my project? What can I do? I already said at the beginning, there are a few companies building this vector databases nowadays. And this company actually have a vector database on the market that you can use. I just wanted to give you a little bit of overview what you can use or which databases, vector databases are available on the market before we maybe look into some kind of use cases, what we can use with this thing. There were a few competitors on the market at the moment. One thing that I really use often is Weaviate. Weaviate is really a database which I can highly recommend because they are pretty mature in what they are doing. This project is completely open source, so you can actually download it. I think it's a patch 2 license or something like this. You can use this, host it on your own premise, on your own system, at home, in a company, on your own server farm. You can actually host this thing, mainly for cost free. They also have, and this is very cool, if you go out and want to test a little bit on vector databases, Weaviate have also a cloud platform where they are hosting it. There are 2 options. You can pay money for this to bring your vectors there, and they are hosting it for you, and you can use it out of box. And the other very interesting thing, they also have a free tier that you can use. So you can sign up for Weaviate, have a free tier, limited to 10,000 vectors at the moment, and they will bin your data after 2 weeks usually. You have to rebuild your database and store the data again. But for the first test that you wanted to do, this might be a good option to try when you're at home, and I think this is interesting for you because this tier is really absolutely free for first smaller experience that you can do. So Weaviate is open source, Apache, so pretty nice to use. We have another company, they call Pinecone. They are very hype at the moment. The problem I see with Pinecone, they are very mature. They are putting a lot of effort in building this vector database. They also have a lot of investment around this, to be honest. And problem with Pinecone is it's strictly cloud-based. So if you are anyway are on cloud and you like this idea of cloud-based solution, this might be something for you. You cannot host it on your premise. It just works in the cloud, which can get a little bit costly over the time, a little bit of warning, but they are very popular and very things. There are another Chroma DB. They are quite new. They have a very cool API, TypeScript clients, and so on. And not really mature, but definitely something will come up in the future. There is Milus, very mature. They also can handle trillions of vectors, which all they can do, by the way. Pinecone, Weaviate, they can all work with trillions of vectors, scales out pretty well over a cluster. And this is also something that I could recommend. When you already have some databases in your company, like Redis, like Postgres as well, okay, I know Redis is not a database, but if you have these tools already in place, there's also some plugins that or add-ons that you can use for this. There's an add-ons for Postgres, for example, which add these vector similarity search that I showed before on top of Postgres database, and the same is for Redis. There you can have this. One thing to say, all these databases usually scale out pretty good. It is not that you have one of these systems, you're scaling out it in a cluster. You have, when you look into Weaviate, you have all the things that you would expect from a database. Nowadays, you have charting of the vectors. You can scale it out horizontally, replication offset to be resilient. And the things, they are based on Kubernetes. You run it on Kubernetes. Everything is fine for you. All the things that we think, resilience, scale out capability, all the things you have in those databases usually and can use them on your premise. Very simple and easy out of the box. And they can really handle trillions of this vector data. If you have trillions of documents, trillions of embeddings, you put it there, you get your results back in fraction of seconds that you have there. And they really scale out pretty good. Just to give you an idea. Very cool thing about this vector database is also we talked a lot of this embeddings that we have, and the question is also how this works and how do you get your embeddings into the vector database. I take you an example of Weaviate just to show you the possibility of this. This is true for most of the things. If you have the Weaviate database, you usually have a client that can create the embeddings by its own. So you can have your client code, which can usually be implemented in Python. Of course, it's machine learning. It can be implemented in Java. For example, in Pinecone, they have Java clients that you can use. You usually also have in all of them JavaScript and TypeScript clients that you can use to query and store your data inside of this. So you have first a client, you have the database that have in storage that stores the data. And the good thing is you have a lot of integrations into this. That means you can put in your API key for Hugging Faces, for Coherence, or for OpenAI, or point it to your own server if you like, they're doing the embeddings for you. And what they can do is you can configure your database to say, when I don't give you any embeddings, forward this to Hugging Face or forward this to OpenAI. Use this model named XYZ on the things to create this embedding. So what you're doing, you're just storing a document or just storing an image, and the databases usually are clever enough to see, well, I don't have embedding, this is unstructured data. They are sending this data forward to Hugging Face, Coherence, to OpenAI, whatever is hosted there, send it and say, make me an embedding for this. You get an embedding bed, and then you're storing this embedding inside of your database, which is pretty cool. And of course, you can also store your own models on a Kubernetes cluster, on your own node, on own pod. In this case, for example, and using this. And this is all not enough for you. You can just code your own code and using Hugging Face Transformer, load the model, get your embedding back in Python or whatever. You're preferring this, and just say, Weaviate, I already have embedding. Don't care about the other competitors. Just put it in the database, and this will work as well. Let's talk about some use cases that you can use to vector databases with. There are actually a lot of use cases that can be used. One of the use cases I've figured out here, we'll see a lot more, is, for example, IDS intruder detection. This is something that you can maybe use also on your projects and on your company as well. Vector databases are very good in doing classifications, of course. If you put them together, they are already clustering and grouping the data with these embeddings that we saw before in these vector databases. And what this is, of course, this is already an automatical clustering and an automatical classification that you do on top of this. So if you have similar data, they are already put together in the same near distance to each other, which gives you automatical clustering of data that you have, and which also kind of automatical classification. You can use this for almost any kind of classification. Let's see, we have an intruder detection system. How you usually would implement this is by, well, you would have a machine learning model, maybe with some dense vector, doing a classic classification algorithm. You have a lot of data about the network traffic that goes on with you. These are already some kind of numeric data that you have, and you want to detect if one of the sessions is an attack that you have. You have an intruder, you have an attack, or most of this will most very likely be a normal traffic that you are running there. What you usually nowadays do, you train your model on top of this, and on top of this data, and you classify it as somewhere in supervised learning process and say, this is an attack, SQL brute force attack, whatever you classify there, and the other ones are normal attacks. And the machine learning model will learn the patterns around this, and actually you will then ask this with new data and say, what is this? You can also use vector databases to do this by using the same models that you have here, and you can actually use this vector to get out of this classification and store this into a vector database. And every time a new traffic comes in, you just ask your vector database, this is a new pattern that I have, create an embedding for this with a machine learning model, and query in the database. And you will see if around this area where your new traffic lies in a vector database, it turns you near to this our just normal activity from user, you were very sure that this network traffic is not an attack on this one. If you find out there are some similar data around this which already have been identified as an attack, you will can say, okay, this is classified as an attack as well. The good thing with all of these things is, of course, might be not the best example, but think about you using such classification models for any kind of things that you have inside of your company. The problem is that I usually see there is you're training your model on such data once in a lifetime, hopefully not, but you're training it once. And then you're asking it, oh, I have a new network traffic. Is this an attack or it is not? But things change over time, right? Then this is true for every data that we are seeing. You're training your model and things change. It works for the first month, I don't know. And if the situation changes, if the data has changed, if everything changed, you have to retrain your model again and again. So usually you need a continuous integration pipeline, something like this, that runs and retrain your model. And you have to observe this if the accuracy is still okay or is not okay or whatever too. You constantly have to retrain models. Yeah? With vector databases, you have CRUD operations. You train the model first to learn this. And if new data comes in, you can just store it in the database. You can update this. If the data is old, you can delete it again in the database without retraining any models. You're just updating your data. You're just deleting it. Yeah? And that's it. Face similarity is another use case. By the way, just if you want to do a toy app on your mobile phone, say image data set, and you can create embedding out of this in a vector, create image embeddings for celebrities, for example, store in a database, have a mobile app. You look in the camera and it will show you celebrities, or you look similar to this celebrity kind of things. Should be another use case. Not very interesting, not very hype. What do we have? Oh, this might be interesting to you. This is something that's called Retrieval Augmented Generation, RAG nowadays. This is what I talked before. When we have ChatGPT, we have all this limitation of ChatGPT, like the token size, like the data that we have. And I promise you I will show you how vector databases can be used to overcome a little bit of this limitation to work with. And this is exactly what we see here on this prompt. Let's think about documents. You have stored a lot of document in text form into a database or products or whatever this is. And you want to ask ChatGPT with a prompt, please create a summary out of this. Yeah? Or please create a Facebook advertisement for my product in the product catalog. You have, of course, to bring your product into this into ChatGPT, and then ChatGPT can find out which is the relevant data of this. And but you have to bring all the data, so the ChatGPT can find out. ChatGPT don't know your data, and ChatGPT don't know current data. This is trained on 2021 or something like this. So actually, you have to find a way how to bring your data in ChatGPT. If you have a lot of data, you run into limitations of ChatGPT. You cannot upload your whole product catalog or your whole document database in this. What you can use vector databases for this, you can do this. You can take your documents, split it up into chunks, like chapters or something like this, which is quite cool. And then you're creating embeddings for all the chapters, and you're storing these embeddings for these chapters into the vector database. There are machine learning models that are trained on answering questions, for example. They are creating embeddings out of this, which are the vectors are similar for the answers, for the questions, and so on. So you can use this, you can chunk your data, document data, in different smaller chunks. Your product database, the same thing. You create embeddings, you store this in a vector database, first of all. Yet no ChatGPT involved, it is just storing the data. The cool thing is, now a user comes in and did a question like, please summarize for Facebook at the data blah, blah, blah. Yeah? Or what is the capital of the United Kingdom, maybe. Yeah? I don't know. Usually you have to bring your own old document database to ChatGPT, which does not work as explained. But what you can do now, the user question came in and asking this question, what's the capital of UK? What you can do first, if you can ask your vector database then, using the same embeddings, and ask them, what is the capital of UK? Question answering, machine learning model doing embeddings. And you ask the vector database, which are the documents in my database which are similar to these questions, which are most likely have the information that I need for ChatGPT. And the vector database will give you, let's say, 50 document chapters or something like this, returns this to you. And this will be the data which most likely holds an information that is relevant to answer this question in ChatGPT. Because semantic context is learned that the chapters in a semantic context, this chapter belongs to this and belongs to this. And it's learned that a question like, what is the capital of UK is most likely found in this document here. So the vector database gives you a list of all this data, of the documents which are not the answer, but most likely will contain the information about what you're looking for. And then you have a chunk of 15 chapters out of your documentation. You put this into a prompt and send this prompt to ChatGPT and say, given this data that I just show you here, blah, 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 please answer the question, please create a Facebook advertisement of this document. And so you overcome the limitation. You just have a chunk of data that you send over and not your whole database to ChatGPT. And you can also limit it so your maximum tokens are not exceeded in this case. This usually works pretty well. It is a welcome pattern that's used now. And it's quite simple. Weaviate, for example, have even an integration in the query language nowadays to say, I want to query data. Did I mention that you also can query the data for embeddings, but also, of course, the structured data that you stored around this. Of course, you can ask for an image and can ask where the photograph is, something like this. So, other point. I think I forgot this. But for the WAG, for example, Weaviate have an integration for ChatGPT nowadays. So you can ask in your query statement, you can say, I have a movie database here. So class is actually a table in Weaviate. You can query all from the movies. I'm interested in the fields with your body. That is here. And then you can say, I do a semantic search for my documents that we've seen before. You give an example for, it can be the question or a similar review in this case for the movie that you're searching for. And this will return of course, let's say a limit of 10 is, bad example, a limit of 10 would return then the 10 documents which are reviews in a movie database, which are quite similar to the one that you put in. And then you can say in the query statement, you can, example here, Weaviate, you can and then use this example with a generative search, and you give it a prompt, which I see here, summarize the following text in a casual form from the field review body. So you can query your database and say, find me similar documents in my database, and when you found it, send this with this prompt together in ChatGPT, and I'm interested just in the result that you get back from ChatGPT there. You will see all the other results, of course. You can query this as well. But it is pretty much integrated in the database here. You can just query it and ChatGPT getting called. I think this is pretty cool. And they already also started Weaviate to create an out-of-the-box client where you can just host it, and it looks in a file folder where the documents are automatically indexing in a vector database, and automatically you do all the stuff there for you, even simpler than this one here. But you see, it's quite simple and easy. And to do this and to use this, and you can come a lot of limitation that you have there. There's another thing. This is they haven't crafted QL API for all of you that don't like actually Java. Might be a little bit better to read what it is, but here again, we're doing near text searches looking for similar vectors in the database, and we are interested in one result, and the result we are sending to ChatGPT to answer us this prompt that we give it. Describe the following Facebook ad. This works pretty well. They have also integration for question answering models, so you can say search all the documents and answer this question that the user has on this document by just using question answering machine learning models. This is actually pretty cool and quite simple and straightforward. Interested so far? Yeah? We have a lot of more use cases. User recommendation system is one thing. You're creating a vector out of it. You're creating a vector out of your product database and use this for user recommendation. This works pretty good, by the way. So this is much more straightforward than using the usual big arrays with user things for this. Other use cases are anomaly detection that we have seen before. You're putting it into, and if the distance to the center of the data that you put in as normal data, you don't need abnormal data, just need normal data, put it in a database, and you see new data, and you ask the database, give me the distance to the data that I already have seen. And if you've seen the distance to the data in the vector database is so long, but here's my cloud of data that I detected as normal or identified as normal. You can see, oh, this is an anomaly. And time series, for example, you don't have to embed it. For example, time series are already numeric values, which is already this kind of embedding. Take a time series, put it in, ask them for anomalies. Works pretty well. Document duplication, you're storing document in your database. Cool stuff. Find before you store it, do I have another document which looks similar? Maybe have another title or something like this, but it's the same document. Do we really want to store that again? Or in batch shop overnight. Yeah? Automatic classification, clustering, you can use it for more use cases. Images to text, you can have models and put in an image in a query or get back text, for example. Tabular question answer I tested works pretty good. You can do a question about Excel tables, movie recommendation, hybrid product search for e-commerce. That means you can look an image on product that looks, I don't know, similar on the image, but and also have some structured data attached to this. Face similarity can use also for this. If you're working for government, maybe this might be interesting for you. Time series usually very hard to handle with LSTM because you have to retrain and retrain and retrain the things. You can use time series as embedding stored in the vector database. And if the data get old or you see that there's some outliers in this, you don't have to retrain your model LSTM-wise. I'll usually do just delete it, and you're done. And many, many, many more. If you look up in the Google, search for use cases, look up on this vector databases, the sites, and we will see there are a lot of use cases where you can use this technology for. So many that I cannot tell you everything in just 16 minutes and explain. Questions, if you have some, but first, before you have the questions, I have one question. Do you roughly now have learned and understood what is similarity semantic search in a high-dimensional vector space? Can I go home and tell this? Yeah, okay. Cool. I think I did a good job here. So, any question over time?
If the microphone works.
Yeah.
I'm not sure if it does. Does this work? Okay. It does work.
Brilliant. I was overwhelming, it seems. Yeah. All very, very good, and everyone understood everything. Oh, there are two. There are two over there.
Thank you. Is there a way to have a query where you can inject some negative request? I want a vector similar to this, but not to this one.
Oh, that is a good question. That would be really a request for the vector databases to add this. To be honest, I haven't seen this yet. I just seen this. Give me the results which are close to this, but I have not seen something like, give me this result, but they are not in this. You have some re-ranking things that you can do, get it back and put it into another model and re-rank it, but I did not see anything like this that you can say, is this near to this, but not in this. In structured data at work, you can say, give me the data which is near to this, and the photographer is not Andy, for example. This works on structured data, on the metadata, but I have not seen this, to be honest, in any database in a query language for embedding. Might be wrong, but I would answer it now with no, it does actually not work. You can have the distance. You can see the distance and say, oh, this is higher than a threshold that I don't want, and you can say, bin this, but I don't think so. Huh?
I think we've got time for one more.
One more, if you have the time, sure.
Oh, okay. I'll come down.
If you're calculating vectors from multimedia sources, do you have to do a normalization between things that have been generated with different models?
When you're storing the data into the database, of course, you have to use the same model for storing the data and when you're querying this data. So the normalization is, of course, upfront. If you have images, for example, and you use a machine learning model, then you usually go on and normalize this in the same scale, wide and high, for example, resolution, and then put it into a machine learning model. The same is, of course, for text, to lowercase, everything like this. You have to use the usual things that you do before using machine learning models, of course, so you get your embeddings out of this. At the end of the day, the vector database just care about the numbers that come out, about the vectors, which this model gives you. So you have to do the usual normalization before it put it into a model. If your model requires this, of course. If you use, for example, BERT, you usually don't require so much of normalization upfront. Or what do you mean by normalization?
It's mainly in the sort of, you were talking about comparing text to media. So if you're putting an image in and comparing it into text space, I'm assuming you're using different models between the two. Is there a standardization that's out there?
There are models which are trained on text and image at the same time. PIP is one of these models. In the training process, you showed this model text as well as images during the training process. And this model learns then, they get text and the task is to find the image or something like this. And you showed them during the training one model, the same model, text and images at the same time to answer the question for this and to get a training. And this model put the text and the images belongs to the text in the vector space into the same area, close to each other. And this is how you're using this. You will have the picture of the Eiffel Tower will be here, and the text Eiffel Tower will be here. And when you're asking for Paris, this one model, it will create an embedding which is some kind here, and it found the nearest result set for the image that I have is this Eiffel Tower things. So you're asking for the nearest in this things and have in the structured data, and it is an image, kind of this. But it's one model that you trained on both task, text and images, and then it works. And it works pretty good, by the way. I just did a workshop on this and we tested it. Works brilliant good. Yeah. PIP is one of these things, a name that you can look up on Hugging Face, for example, which is one of this model trained on text and image.
I think that's probably all the questions we have time for. But yeah, thank you very much. Thank you.
Thank you.